Today we'll jump into the two-dimensional defects and the three-dimensional defects that can be present in a material. So let's start our discussion with the possible two-dimensional defects. Two-dimensional defect is also known as surface defect, right? Because a surface is basically a two-dimension. So what are the possible type of surface defects? It can be an external surface, the ending of the specimen, right? So any specimen will end somewhere abruptly, so it has an external surface. Then there will be grain boundaries. I have already discussed about grain boundary in previous lectures, but I'll go and discuss about it in further details today. And then we have something known as twin boundary. It's a special case of grain boundary. So let's start our discussion with external surface. So as the name suggests, and as I said, external surface is basically the ending of the specimen, right? The external surface of the specimen. So what happens is that normally if there is an atom, it will have a coordination number. Let's say we have a FCC kind of atom, then it will have a 12 coordination number, which means there will be 12 bonds attached to it, right? 6 in this plane, 3 top and 3 bottom. That will make the 12 bonds for this atom, and when all the 12 bonds are present, it is surrounded by all the possible atoms in all the possible directions, right? But what happens at the surface? When we have surface, an atom at the surface will have less than the maximum number of possible bonds. Thereby there will be loosely hanging bonds, there will be free bonds, and free bonds means higher energy, because bond formation leads to release of energy, thereby lowering of energy. That's why basically bonds are formed, in order to lower the energy. But the external surface atoms will have free bonds, thereby they will have higher energy. Therefore, as I have written here, external surfaces are regions of high energy because they have free bonds. And the ideal case, the material would try to minimize the surface, external surface area. Therefore, during solidification, what will happen is they will try to solidify in a spherical manner, right? But once the solid is there, it is intact, and there cannot be any possible changes in the surface area. Okay, so this gives you an idea about external surface. And why is this called a defect? This is a defect because basically the atoms does not have the type of bonding which it is supposed to be if it were in the bulk, right? Now let's jump into the more important type of two-dimensional defect, that is the grain boundary. If you remember correctly, I have discussed that any material is composed, any crystalline material is composed of many grains, right? There will be different grains like this, and each grain will have a particular crystallographic orientation. So something like this, and the change in crystallographic orientation is basically the boundary where the change of crystallographic orientation takes place is known as the grain boundary. So between this and this grain, there is a change in crystallographic orientation over here, and a change in crystallographic orientation over here and here. So these are the grain boundaries. Grain boundaries are basically regions which are separating two different grains or crystals. Okay, and as I already discussed, different crystallographic orientation is present in different grains. Then grain boundary region is basically then what it is? It is the region of mismatch leading to transition from one orientation to a different orientation. Okay, in terms of atomic arrangement, if you think, suppose in one grain we have atoms perfectly arranged like this, right? Perfect arrangement of atoms like this. But in the adjoining grain, the atom arrangement changes. So like this, right? So what is happening here, the orientation is in this fashion, whereas here the orientation changes to this fashion, and a clear demarcation over here takes place where the atoms are not exactly located where they should be, either from the atoms of this grain's perspective or from the atoms of this grain's perspective. There is an internal region where the atoms are randomly placed. They are not perfectly aligned with the grains. So this region is basically our grain boundary region. We can have two types of grain boundary. We can have low angle grain boundary, or we can have high angle grain boundary, and that will depend on the degree of misalignment. If the grains are almost similarly oriented, but there is, let's say, a misorientation of around 4 degrees, 5 degrees, then this falls under the low angle grain boundary type. But if one grain is like this and the other grain is like this, then what is happening? We'll have a very high angle of misorientation. This theta is very high, and then this is a high angle grain boundary region. Okay, now grain boundaries can come in two variety. One is the tilt boundary and the other is the twist boundary. What is tilt and what is twist boundary? Tilt boundary is basically formed by edge dislocation lining up. So there will be several edge dislocation like this. Okay, and atoms are arranged like perfectly over here and perfectly over here, but the misorientation is taken care of by a series of edge dislocations in the grain boundary region. Whereas a twist boundary is something where instead of edge dislocation, the misorientation is taken care of by screw dislocations. And how does the misorientation take place? Here the atoms in the tilt boundary, atoms are like this and this. In the twist boundary, basically you can imagine this as atoms are arranged perfectly here, and there is another cube, okay, another cube like this, where again the atoms are perfectly arranged, but this cube and this cube are inclined at an angle to each other, right? So basically there is a twisting of the atoms. The atoms in this arrangement is twisted with respect to the atoms is in this arrangement. So basically you just provide a twist for all the atoms, and this can be taken care of by a series of screw dislocations. Okay, so these are the two types of grain boundaries that can be there. And obviously the amount of energy that is present in a grain boundary depends on the amount of disorientation, the degree of disorientation. Larger the degree of disorientation, more will be the number of dislocations to take care of the misorientation, and more will be the amount of energy in the grain boundary. Fine. Now as I said, that grain boundaries are region of higher energy because there are defects present. There is ununiformity. Therefore, since it is a region of higher energy, it is also a region of higher activity, higher chemical activity. Why so? Because by high chemical activity, the grain boundary region tries to reduce its energy. It tries to pull down the energy and attain a more stable state. For the same reason, impurities tend to segregate at the boundary. If there are impurities present in the material, they will try, if like suppose these are different grains, then the impurities will come and settle at the grain boundaries. Because these are already regions of high energy, and the impurities, if present in the bulk, will lead to higher energy. So they rather sit at already high energy region and thereby reduce the effective energy of the whole system. And finally, as we have seen that grain boundaries are region of higher energy. Therefore, if the total effective surface area of the grain boundary is less, then the effective energy of the system will reduce. And how can we reduce the total surface area? We can reduce the total surface area if instead of many small grains, we have less number of coarser grains, right? So the effective surface area will be reduced by coarsening of the grain, which is known as grain coarsening. And this is one of the methods which is used to reduce the surface energy of the due to the grain boundaries. Okay, So just to sum up the idea that grain boundaries are regions of mismatch of crystallographic orientation, and they are a series of either edge dislocation in tilt grain boundary or screw dislocation in twist grain boundary. Grain boundaries are also region of high chemical activity. Okay, with this background, let us see the third type of two-dimensional defect. The third type of two-dimensional defect is a special kind of grain boundary. It is known as twin boundary. What happens is, we have seen in the case of grain boundary, there is a misorientation, right? But in the case of twin boundary, there is a symmetry in the misorientation. That is, this image represents a twin boundary. What is happening is that this is the twin boundary, and for every atom in this grain, there is an equivalent atom, a mirror image, if you would like to say. So they exist in pairs. For every atom here, there is another atom in the other grain, right? So a special type of grain boundary with mirror symmetry about the twin boundary rather. Now, how does twin boundaries form? There are two types of twin boundaries. Twin boundaries can either be formed due to stress, which is known as mechanical twin, or it can be formed during annealing treatments, which is known as annealing twin. Okay, so these are the two types of twin boundary. They are having the same properties, but just their formation, reason of their formation is different. And twin boundaries occurs in certain defined planes and directions. And what defines the plane and direction on which the twin boundary will exist? It depends on what crystal structure we are discussing about. We are not going to go into the details about twin boundary. I just wanted to introduce you to the idea that some symmetry can even be present in the terms of twin boundary. Okay. Now let us see some other two-dimensional defects that can be present. Something that is known as a stacking fault. Then we have phase boundary. Then we have what is known as domain wall. Let me briefly explain you. Stacking fault. I have said that ABC arrangement is present in FCC crystal, right? Suppose it so happens that ABC, AB, ABC, and further it continues ABC, ABC. So here effectively what is happening is there is a fault in the stacking sequence, right? The C layer is absent here. So this type of defect due to a change in the stacking sequence is known as a stacking fault. Okay. What is a phase boundary? In grain boundaries, what happened is that there were different grains of the same material, of the same phase, but it can so happen that the two grains, surrounding grains, belong to different phase, right? One can be ferrite and the other can be cementite. These are we'll discuss about ferrite and cementite in iron while discussing about steel. But for the time being, let me say that ferrite is one phase, cementite is another phase. Ferrite is basically alpha iron and cementite is FeC3. Okay, so if there are two different phases present, then the region boundary separating them will be known as phase boundary. Fine. Now what is a domain wall? A material can be magnetic, right? So let's assume that we have a magnetic material and there will be different regions in the material which will have magnetic orientation in different directions, effective magnetic orientations in different direction, right? So the regions, the boundaries separating these different orientations are known as the domain walls. These are different domains of different magnetic domains. So the boundaries separating them are known as domain walls. So these are the different kinds of two-dimensional defect that can be present. Now let us see briefly what are some of the three-dimensional defect that can be present in a material. Three-dimensional defect are also known as volume defect because a volume is basically 3 dimensions. So what can be different kind of volume defects? One can be pore. There can be porosity in the material. Then there can be cracks, right? There can be cracks through the material which are not supposed to be there, but it is there. Then there can be presence of completely different material as in they are known as foreign inclusions. So we have something like this with different grains of the same material, but then we have some inclusion here. So this is a three-dimensional inclusion. Therefore it is a volume defect. And there can be other phases present which should not be there, right? And what are the causes of volume defect? Volume defects mainly occur during the processing and fabrication stage itself. So once it is introduced in the material, it stays in the material. Also, problems like cracks can occur due to usage. Continuous usage can lead to crack formation. Okay, so this kind of brings you to the conclusion of the series of lectures introducing you into the concept of imperfections in solid. These ideas about the different type of imperfections in solid is quite fundamental to understanding how the property of a material varies, or how we can tweak the property of material by using the different kind of imperfections, by introducing different kinds of imperfections.